Okay, so thanks everyone for coming back for this last lecture. And we're talking about geometric topology of three manifolds. And after the last class, many of you probably thought, wow, this is a nice ending for the course. Because I mean, we prove geometrization basically. We give an idea of what geometrization is important. And there's some echo here. Echo? Let's just keep going on. And it was a nice ending for the course. It could be the end of the course. Because I mean, you have a closed tree manifold, and then you decompose it by spheres, you get prime factors. Then prime factors are either S2 plus S1 or they are irreducible. If they are irreducible, you decompose by tori using the JSJ decomposition. Then you remove these twisted bundles over the fine bottles. You get the geometric components of your decomposition, and they are either cipher fiber, toroidal, or torus bundles. Torus bundles are geometric with geometry sultry. Cipher fiber manifolds are either infinite pi 1 or finite pi 1. If they are infinite pi 1, you have 5 cipher fiber geometries. And if they have finite pi 1, is the elliptization theorem. And if they are toroidal, which is what's left, they are hyperbolic geometry. So this is awesome. What else can we say? How can I keep going? The thing is, we can say a lot more. Geometrization is awesome. It's beautiful. But actually, to pick up a manifold in your hand, like, yeah, this manifold, which geometry is it? This is not easy. So let's start going after geometrization. Especially today, we will focus on the richest of all geometries, which is hyperbolic geometry. So first, let me show this classification. If you have a closed or readable manifold, and we know that it is geometric, so we can classify the geometry in terms of pi 1, of its fundamental group. There is this huge theorem here, where you can say if pi 1 is something, then you know that geometry is that. And what I want to show you is not the classification itself, but is the otherwise case. If you are nothing as the previous one, if you what's left is hyperbolic geometry. And that's a first hint that hyperbolic geometry is the richest of them all. Is the geometry which is more complex, which has more examples. There are several other things that point to that, that actually prove that generically a geometric manifold is going to be hyperbolic. But this is just a first, how to say it, evidence. Okay, so yeah, hyperbolic geometry is the richest, but sometimes to pick up your manifold and to compute its fundamental group is no easy task. So we need to have a better classification. We need to have a better way of looking at a manifold and understanding whether it is or it's not hyperbolic. And that's today's topic, basically. So in the rest of the talk, we'll focus on hyperbolic manifolds, which will either be closed or be non-compact, and with an extra assumption, which is basically because this course, they have finite volume, because the hyperbolic manifolds that appear on geometrization will have finite volume, all of them. I need to say that there are hyperbolic manifolds of infinite volume, but they don't have toroidal boundaries. They will have higher genus boundaries, and they don't appear on geometrization. But they are also interesting from the geometry point of view, at least. Okay, yeah, and actually we will kind of ignore the closed case. We will focus more on the non-compact finite volume case, which is something that I love, and actually was the reason why I started studying geometric topology, was to understand the topology of finite volume hyperbolic manifolds. So the first main objective of this talk, and actually is the rest of the important part of the course, is to present Thurston's hyperbolization criterion, which is an algorithmic point of view to know if a manifold is or isn't hyperbolic. So let me present some theorems about hyperbolic tree manifolds of finite volume. First, if you have a complete, orientable, non-compact hyperbolic tree manifold of finite volume, then it is diffeomorphic to the interior of some compact manifold with toroidal boundary, with and the interior is diffeomorphic to the interior. Did I say that? I think I said. So it's going to be diffeomorphic to the interior of a compact tree manifold with toroidal boundary. And from now on, we will focus our attention to this kind of setting. M will be a compact tree manifold with toroidal boundary. And yes, right. And the metric in the interior of M is complete. So you cannot exit your manifold unless you spend infinite energy. In particular, the boundary torus is something that is not there. It's going to be at infinity. It's going to be called an end of your manifold. To reach the boundary of your manifold, you would have to go like infinite distance. So you will never actually catch the boundaries at infinity. Yeah.
There can be more than one toroidal bond. Right?
Of course, there can be finitely many toroidal boundaries, because if you have infinitely many, you have infinite volume. Each toroidal boundary will have some definite amount of volume. Okay, let's make some description of hyperbolic tree manifolds of finite volume. The first one is the definition description. It's basically useless. A Riemannian tree manifold is hyperbolic tree manifold of finite volume if it has a complete metric of constant curvature -1 and finite volume. This description doesn't describe anything, but that's the definition from the point of view of Riemannian geometry. And I started with this one. I had no idea what this objects were. And so let's go with the description from the point of view of hyperbolization. A compact, because now we know that it's got to be compact with toroidal boundary. Compact irreducible tree manifold is a hyperbolic tree manifold of finite volume. If it has toroidal boundary, pi1 is infinite, it's atoroidal, and it's none of these three counterexamples which appear in the proof of the geometrization. So again, that's a nice characterization, but it's kind of hard. It's kind of difficult to actually show that a manifold falls into this description, especially when it comes to being atoroidal. Okay, so let me give you a geometric description, and now it's not a definition. These two basically could be used as definitions, but this is a description. How do these manifolds look like? What's the appearance of a hyperbolic tree manifold of finite volume? It's like that. What is this picture showing, basically? You have something called a thick part, and what is thick? Thick means the injectivity radius is larger than some number. You choose a small number, like I'd say 0.1. And there is a compact part of your manifold where the injectivity radius is larger than 0.1. This is called the thick part of your manifold. And just to remind you, what is the injectivity radius is for a given point, you look at the tangent space, and you look at spheres, let's draw disks, and you look at the exponential map. So you have an exponential map from your TPM to your manifold M, and this focus bad. So the injectivity radius is the maximal radius that you can go, and your exponential map is still a diffeomorphism. So when it's no longer a diffeomorphism, something like this, well, no, the other way around, right? Bad draws. Something like this will happen. So if you are larger than your injectivity radius, you would have something intersecting, because you are hyperbolic. Because you are hyperbolic, so the exponential map is really well behaved. Okay. So you have this thick part, and what's left in your manifold are called the cusp ends. It's a finite number of ends, a finite number of boundary tori, where you are going to infinity, and the volume of this is really small, and the injectivity radius in these ends is also really small. It's less than the constant, like 0.1 that you chose. For any constant sufficiently small, you have this thick decomposition. Okay, so how are these ends? And this picture for me was something that helped me a lot the first time I was making geometry in these spaces. These ends, like this called these cusp ends here, all of them, they look the same. All of them are just the quotient of a horoball in H3. A horoball in H3 would be something bounded by a horosphere. And we can use the half-space model because it's the easiest to see this correspondence here, where horospheres are horizontal planes. And now you take just two parabolic translations, linearly independent, and you make the quotient of these planes by these two translations. So when you take R2, divide by two translations, you get a torus. And that's your decomposition by torus. It's basically your toroidal boundary here, but it's actually at infinity because you will see torus, 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 torus. At every slice, you see a torus going up to infinity where your boundary would actually be. So that's a description of how these manifolds look like. Example to keep in mind, knots and link complements. So let P be an orientable closed tree manifold. P is not going to be the hyperbolic example. P is going to be an ambient space where you can see your hyperbolic manifold inside that ambient space in some sense. And what is a knot? A knot is just an embedding of S1 into your manifold. You just take any closed curve there, and it's going to be a knot, simple closed curve, embedded. But obviously, we want it to be like kind of interesting. The trivial examples are also knots, but if it's knotted, it's more interesting from some point of view. So that's a knot. And you also have links. Links are just disjoint union of knots. And we are basically in topology, right? So you take any link and you move them a little bit. If you don't intersect, if you don't break it, it's going to be the same. So officially, you could think of isotopy classes of these guys here. They will be all equivalent. Okay, so some knots and links in S3 here are how many? 8 examples. 8 examples of knots and links in S3. The first one here is the unknot, like it's not knotted. It bounds trivially at this because the most trivial embedding of S1 into S3. The second one is the trefoil knot. It's the knot with the least number of crossings. Everything that you are seeing here, they are projections of knots and links into this plane, right? We are in R3 in our world, and R3 and S3 aren't very different. You just add infinity to R3, and then you have the tree sphere. So we have here this projection, this plane, this screen is S2. This screen is S2 because the plane that contains this screen goes to infinity, so it's S2. And these drawings here, they are called projections. So once you have a projection, you have a crossing of your link if you have one component going above or below the other one. And this knot here is called the trefoil knot, and it is the knot in S3 which is not trivial, with the least number of crossings. If you have anything with less than 3 crossings, it's trivial. You don't need any crossings at all. Here you have one of the most important knots in S3, which is the figure 8 knot. This one was studied a lot, like a lot, really a lot. Here you have an example of a link, because you have two components, have two knots, but it's a link because they are linked together. It's intuitive to understand what is to be linked together. In S3, there is a simple definition, which is they are disjoint, but they cannot be separated by a sphere. So they are linked together. And this is the Hopf link. This is the simplest linked link that exists. And here we have the Riemannian rings with three components, the number E. Here you have a chain. Here, how many components? We have a 7-component chain and three twists in it. So it's called a 7-3 chain. Here you have something called a composite knot, like you take two knots and you do basically a connected sum of these knots, and you get this composite knot. And here you have a link that is unlinked. You have two knots which are separated by a sphere. You can think that there is a sphere around this one that separates it from the other components. So it's not a linked link. Okay, but why knots and links? That's a reasonable question to make. Just because they are pretty? No, not just because of that. Whenever you have a knot in your closed free-manifold, you can look at a tubular neighborhood around this knot. So your knot is S1, topologically S1, so it's a simple closed curve. When you take a sufficiently small tube around S1, that's going to be a solid torus. No matter if it's knotted, no matter if it's wildly embedded. A tubular neighborhood, if it's sufficiently small, it exists, and it's going to be a solid torus. And the boundary of the solid torus is a torus. It's a 2 torus. And that's what we want the boundary of our manifolds to be. So if you take the complement of a neighborhood of this knot, you will obtain a compact trimanifold with torus boundary. In this case, because K is a knot, it's just one boundary component. But if you take it, if you do the same thing with a link, you get more boundary components. So in the previous slide, if you take any of these knots and links here in S3, and you look at the tubular neighborhood around them, and you remove that tubular neighborhood of the manifold, you get a compact trimanifold with toroidal boundary, and as many boundary components as you have link components. For instance, here, the Hopf link, you have a manifold with 2 boundary components. Here, the Riemannian rings, you have 3 boundary components. So these are actually the best candidates to look at if we are trying to obtain hyperbolic trimanifold hypervolume. Remember, here I only showed examples in S3, but in general, you could do the same thing in a general closed trimanifold. Things get a little more complicated to visualize, but they are really nice. And actually, not only perfect candidates, but the only candidates in some sense. Any hyperbolic trimanifold of finite volume non-compact can be obtained like this. P can be wild, can be hard to get. You don't have a single way of looking at hyperbolic trimanifold as a linked complement. You might have, I think you have infinitely many ways, right? You have infinitely many P's where you can have links whose complements are the same thing as your hyperbolic manifold. Yeah, but since we are trying to get examples, these are the candidates. Think of P, think of a link, think of the complement of a tubular neighborhood of this link, and it's going to be a real nice model for you to work with. So here's just a convention. P will always denote an orientable closed trimanifold. M will be a compact orientable trimanifold with toroidal boundary, non-empty, and we will think that M is P minus the neighborhood of some link. Yeah, and that's the definition that I was looking for. We will say that the link is hyperbolic if M is hyperbolic, in the sense that the interior meets a complete hyperbolic metric of finite volume. So now we have a notion of hyperbolic links. Now we have a notion of hyperbolic knots. Okay, so let's characterize hyperbolic manifolds of finite volume in a few seconds, just a definition before. A compact surface embedded in a compact manifold, it's going to be proper. I already said that, I think in 2 classes ago or in the last class or something, but let's repeat it. If the boundary of sigma is the intersection of sigma with the boundary of your manifold. In other words, you don't have boundary of sigma on the interior of your manifold, and you don't have interior of sigma on the boundary of your manifold. That's the definition of being proper. We will let I be the inclusion map. We can see sigma inside of M. And sigma is called incompressible if it's not the disk, if it's not the sphere, and if this inclusion map is injective on the fundamental groups. So in other words, if you have a non-trivial element on the fundamental group of your surface, it has to be a non-trivial element in the fundamental group of your ambient space after picking base points. And what happens if it's not incompressible? If it is compressible, then you have an element here, which is trivial in the ambient space. So you can prove that actually there is a disk, which is bounded by that curve. So the boundary of D is in sigma. And actually, I should have said that the boundary of D equals the disk intersection with sigma, like being proper, but for disk and sigma. And the boundary of the disk is non-trivial in the inner surface. And we can redefine being a toroidal for this setting. M is a toroidal if every incompressible torus, now we know what incompressible means, is homotopic to a component in the boundary of your manifold. So that's being a toroidal. And more precisely, this is basically the definition of being homotopic. And here there is a word that geometers don't like: continuous. We don't like this word, because for any differential geometer like myself, everything should be smooth, like infinity and probably analytic. You think of something, if it's not analytic, you crash, you bug, your head doesn't work. Like the other day, I was looking at something which was C2 but not C3, and I was like, huh? I don't understand this object. I can never understand object that is C2 but not C3, and I can't understand continuous things. I cannot understand anything continuous. It's got to be at least infinity. So yeah, I don't like this word and I don't like this definition. So let's make it a little better. So let's improve being a toroidal. We will lose something, but we'll gain a lot. So let T, now this torus here is any torus. It could be just immersed, it could have self-intersections. And now we will work with embedded torus. So let T be an embedded torus in M. And we say that this torus is boundary parallel if it is isotopic to a boundary component. So now there is something that I can understand. Isotopies, they are like homotopies, but for each slice, you are a diffeomorphism. So your torus moves as a geometer would think that it moves. It moves nicely in your ambient space. It doesn't go crazy and crosses itself and then does something else. I cannot even think of an homotopy that is not an isotopy. It's hard. Okay, in particular, if it is isotopic, there is a torus boundary. And this torus boundary, together with your torus, they bound a region. They bound a product region. You have This, like the example of the, how did I say that? The cuspens, these torus here, they are all isotopic, and they are isotopic to the boundary. So that's the idea of a boundary parallel torus. And now we can say what is to be geometrically atoroidal. It's not the same as atoroidal, but sometimes be careful because some people think use the same definition for both. If you're reading a geometric topology book, please always watch what they mean by atoroidal, because they might be thinking geometrically atoroidal. Okay, so it is geometrically atoroidal if every incompressible torus is boundary parallel. So it's a little different from being atoroidal, because now you have not embedded, you have any torus, incompressible torus, and it's not isotopic to a component in the boundary. It's not homotopic to a component in the boundary, it's isotopic. And so every atoroidal manifold is geometrically atoroidal, but the converse is not true. You have examples of geometrically atoroidal manifolds which are not atoroidal. I will show you one example now. Okay, you look at the parapents. Let X be the parapent, which is, if you recall, the disk minus two little disks, where you would have the waist and the two legs. But here I am thinking as the parapents of the disk minus 2 points, the same thing. And now you go with the product of this parapents times S1. So you have the solid torus minus 2 circles, and these circles are not linked together. They're the most basic circles you can think of. Okay, this manifold is geometrically atoroidal. How do you prove that? It's really simple, because it's geometric. Proving that something is geometrically atoroidal is a lot simpler than proving that it is atoroidal, unless you can compute the fundamental group. If you can compute the fundamental group, then proving atoroidal is easy. But why is this the case? Because if you have any embedded torus in this manifold, it is also an embedded torus in the solid torus. Like, forget the two circles. You have an embedded torus there. An embedded torus in this solid torus separates. Always gonna separate. It's gonna have two distinct components. But let's see if I write down. No, I just write down this. Now it's gonna have two components. But we are assuming that this torus is incompressible, because that's what you need for geometrically atoroidal. For it to be incompressible, at least one of these two circles must be inside the torus. Define one of the regions inside, the other outside. The region that has this outer boundary, we call it the outside of the torus. The region that doesn't contain is the inside of the torus. So at least one of this is inside the torus. And now the torus goes around it. So it's boundary parallel. It's either boundary parallel to one of these components, either you have only one component inside the torus, and then the torus is going to be boundary parallel to this component, or you have both components inside your torus. And now it's going to be boundary parallel to the outside. You have these product regions. You either have a product region, think of this as the torus. You will even have a product region to the inside, or if the 2 points are inside the torus, the 2 circles, then it's boundary parallel to the outside circle. So this manifold is geometrically atoroidal. But it's not atoroidal. Yeah, that's what was the example, right? And why is not atoroidal? I cannot. I had to cheat. The first time I saw this example, I was like, and here is the curve. Here is your torus, which is not embedded, it's just immersed. and it's not boundary parallel. And these arrows are the orientation of this curve. Like you start here, let's start here, and then it goes around like this and closes up. This times S1, this curve I'm drawing is an S1 curve, not embedded, but it's a closed curve, S1. And now I make it times S1, it's a 2 torus, and it's not homotopic to the boundary. You can never avoid one of these two curves if you want to make it homotopic to the boundary. Okay, but the good news is that there are a few examples. I said that improving a toroidal to geometrically toroidal, you lose something, but you gain something. You gain intuition, you gain geometry, but you lose some counterexamples, which are not toroidal, which are small cipher fiber spaces. And the definition of small cipher fiber spaces is that the number of singularities of the base orbital and the number of boundary components is less than or equal to 3. So those are the only examples, like this one, right? This is a cipher fiber space. This parapents times S1, you have circle, 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 circle. You have this foliation by circles. And you have the, oh, it is a product. It's the most trivial thing that you can have as a cipher fiber space. Is a product of the parapents with S1. And the base orbital is going to be a surface, it's going to be totally smooth. And it's going to be with the parapents, which has 3 boundary components. So it's a small cipher fiber space. Okay. Now let's go to.
Hello, I have a question.
Yeah.
So when you blew x, like x is a disk minus 2 point. So if I do top and bottom, means x plus I, and take the top part and bottom part and blew 180 by 180 rotation, yes, then it will be geometrically.
I'm not understanding.
So your x is disk minus 2 point, and m is yeah. So I am taking x plus I interval. Okay.
No, x plus x plus S1.
Okay. Instead of gluing identity homomorphism top and bottom, I am gluing top and bottom by 180 rotation.
Oh, by rotation.
Yeah. Then
it's going to be a cipher fiber space again, because you still have the fibers.
Yeah, it will be a cipher fiber space, but yeah.
I don't know, but probably, if my intuition is right, I think they will be isomorphic. I don't think you will change anything here. In this case, you are just twisting this 2 lines. You are rotating these 2 lines, like they are going up and they are rotating again. But it's the same thing. You have a solid torus minus 2 curves, and these curves are not going to be linked. So I don't know. I never thought of that example. Later we can talk about it a little more.
Okay.
Right now, I don't think it's.
Thank you.
Okay. Okay, so let's go to essential surfaces. Yeah, essential surface. We say that a surface sigma properly embedded in M is essential in these conditions. There is another definition for essential surfaces, but I want essential just in these cases, so that's my definition here ad hoc for essential surfaces. If sigma is topologically a sphere and it doesn't bound a ball, it's going to be called an essential sphere. If sigma is a disk that the boundary is non-trivial in the boundary of a manifold, this is going to be called an essential disk. If sigma is a torus that is incompressible and not boundary parallel, then it's going to be an essential torus. And if sigma is an annulus that is also incompressible, and not boundary parallel, this is going to be an essential annulus. And these definitions, they are good in some sense because everything is embedded. So it's geometric definition. This is a geometric definition for essential surfaces. And finally, I can present to you Thurston's hyperbolization criterion. And this is the main theorem I'll show you today. Suppose that M is orientable, compact, with non-empty toroidal boundary. So he is looking at hyperbolic manifolds of finite volume. Then M is hyperbolic if and only if it has no essential spheres, no essential disks, no essential tori, and no essential analyte. That's it. This criterion is inside my heart. Because we can check it. We can check this. We can take our manifold and we can look, do we have an essential sphere? If you don't have any essential sphere, nice. Now you look, is there any essential disk? You try to look at the spheres, no, we can prove that there are no essential disks. Are there any essential tori? Embedded, they're nice. No, so look at analyte, and this is the hardest part, usually. And if you don't have any essential analyte, then you are hyperbolic. You don't have the hyperbolic structure in your hand, so it's different from other methods where you can like try to solve some equation and triangulate your manifold and explicitly find the hyperbolic metric. But you know that there is a hyperbolic metric. And for geometry, that's all you need. The existence of some hyperbolic metric, most of the times. And this is just a repetition of the previous description of hyperbolization. And I'm going to give you just a brief overview of why, if you have a manifold that satisfies these four conditions, then it is hyperbolic. Just one way, but it is if and only. Okay, so assume that it satisfies Thurston's hypothesis, and let's prove that it is hyperbolic. So what do we need to do? We need to prove that it is, that pi1 is infinite, and that it is a toroidal and not one of these three examples here. Okay, first, no essential spheres is the definition of being irreducible by definition. We are just making it like a little more elegant. I love that. Yeah, four things. One of them is being irreducible, but we are changing it for no essential spheres. No essential disk rules out D cross S1. D cross S1 has this, here is disk, cross S1. So you have this disk, which the boundary of the disk is non-trivial on the boundary of your manifold. The boundary of your manifold is a torus, and this curve is non-trivial. So this is an essential disk. So no essential disks rule out this possibility. Non-empty toroidal boundary, since your M has non-empty toroidal boundary, and you are not D times S1, this proves infinite pi1. Actually, D times S1 also has infinite pi1, so yeah. I think yeah, that's final volume. And no essential torus is almost a toroidal, except for small type of fiber spaces, and no essential analyte kills the rest. Which any small type of fiber spaces will have essential analyte, and these other two manifolds also will have essential analyte. So that's the idea of why these conditions imply hyperbolic, but it's an if and only if. Yes, well, basically, the course is over. Basically, that's all about geometric topology of three manifolds, but let's go a little further and tell you a little bit about applications. First, knots in S3. That's where it all started. That's actually where all this geometric topology of three manifolds started. People were looking at examples. Yeah, let's try to find examples of hyperbolic three manifolds of finite volume. And it was really, really difficult. Nobody could find examples. They had like one or non-orientable example, the complement of the figure 8 knot. And then Thurston comes up. And Thurston said, the complement of the figure 8 knot is hyperbolic. So maybe there are other knots which are hyperbolic. And oh, too bad I cannot return a lot because it's too far away. But you remember I told you that the simplest knot, which is this is not. Yes. I can no longer draw the triple knot. There was a time that I could do it with my eyes closed. Mm-hmm. I forgot how to draw the triple knot. The triple knot, the easiest knot that there is with 3 crossnuts, it's not hyperbolic. And that's what made hyperbolic geometry to take so long to advance. If the triple knot were hyperbolic, people would have found that most knots are hyperbolic. But the first example, the simplest one, was already not hyperbolic. Just a figure 8 knot was hyperbolic. And the others were really, really, really hard to make the computations. So people, they thought, yeah, maybe let's try stuff. Yeah.
No, I just want to make a historical comment.
Sure.
So this person called Bob Rayleigh. Rayleigh was the one who first showed that
the figure 8 knot had hyperbolic complement. Yeah, exactly. Thank you. I was forgetting his name. I was actually thinking, what's the name? Rayleigh. You're right. Thank you. And then, well, so let's talk about knots in S3. Then Thurston comes up and I will look at all the knots and see which ones are hyperbolic using his criteria. So Thurston found out this theorem. Any knot in S3 is either a torus knot, and a torus knot is a torus, just like in this picture, that can be isotoped to a boundary of a torus in S3. So it's something that, it could be knotted. This torus could be knotted. This is an unknotted torus and a torus knot that is to the boundary of this torus. A satellite knot, which means you have some knot, any knot that you want, and you have a tubular neighborhood of this knot, and your knot goes inside this tubular neighborhood doing something more weird than the original knot. Like this one, this knot here, it is in the boundary, in a tubular neighborhood of a trefoil. So if you think instead of 2 curves going around and crossing themselves, just one curve, this would be a trefoil knot. And a satellite knot is something that goes around this trefoil knot or any other knot, doing weirder stuff. And you don't have a way of isotoping it to lie in the solid torus minus a disk, right? You don't want you don't want it to be simplifiable in some sense. And so you are either a torus knot, a satellite knot, or a hyperbolic knot. So he classified every knot in S3 in 3 classes. And the trefoil knot is a torus knot. Okay, just a basic idea why that's the case. These manifolds, they never have essential spheres. Because if you have a sphere in S3 minus a knot, the sphere is in S3. In S3, this sphere separates in 2 balls. And the knot is either in this ball or in the other ball. If the knot is in this ball, the other side is a ball. If the knot is in the other, then this one is a ball. So any sphere bounds a ball in this manifold. If there is an essential disk, then you can see that your knot is unknotted. So it is a torus knot. Anything that is unknotted ends up being a torus knot. If there is no an essential torus, you can see that it has to be a satellite knot. And this is the hardest part, a little more difficult to see. But if there is an essential annulus, then you can prove that you are, again, a torus knot. Torus knot is a PQ curve. And you can see that you use this essential annulus to make an isotopy inside the boundary of the torus because it's incompressible. etc. Okay, so first example, the unknown. So this is the unknown in S3. It's not hyperbolic because you have an essential disk. That's an essential disk in your complement of your manifold. This is one I like. It's not going to be hyperbolic because you have an essential annulus. This blue thing is an annulus. The boundary of your annulus is in the boundary of your manifold. And remember, the manifold is everything but this link. So this link is the boundary of your manifold. You have actually, it's not the link itself, but a tubular neighborhood around the link. So you have two tubes, and this blue thing here is an annulus. It's going to be punctured by this red curve, by this. So you are removing a disk from a disk. So a disk minus a disk is S1 cross an interval, and that's an annulus. So it's not hyperbolic, but what I like about this link is that you can actually understand the topology of the complement. It's a nice argument. Let's look what is the topology of this complement. It's easy to see. Start with S3, and you have your first S1. Remember, oh, no, other way around. Remember, this is the Hopf link, and we have a red curve and a blue curve. Now I will think that this red curve, we are in S3. And I told you already a couple times, S3 is basically equal to R3 plus a point at infinity. And we are thinking that this red curve passes through that point at infinity. So this curve here, this red curve, is going to look like this, like a straight line in R3, infinite line, a vertical line. The other component cannot go through infinity because they are disjoint, and the point at infinity is just one point. So the other component is this one. It links. It has to link. This is the Hopf link, so it's going to be this one component here. Now, how can we understand this topology of this complement? Let's look just at the plane of the blackboard. So here, let's think of this blue curve as going outside the plane and then on the back. It's like this. The intersection of this vertical plane with the Hopf link, the plane that contains this line, is like this. You have the whole red line and two yellow dots. Now you can see that this thing here has this foliation. Actually, I shouldn't have drawn the left side of the foliation. We are just interested in this right side of the picture. This right side of the picture is, well, this is foliated by circles. S2, yeah. Right. What? I'm sorry? That's right? Yeah. So this right side is just an interval 0, 1 cross circles. For any point in this interval, you get a unique circle. Look here. Here I have 0, 1. For each point in this interval, you have a unique circle. So this half part, this right part here, is just S1 cross 0, 1. But now your manifold is just take this part here and you rotate, make times S1. So S3 minus L is going to be S1 times that half part, that's the plus there. So it's going to be S1 cross S1 cross 0, 1, and S1 cross S1 is T2, and 0, 1 is R. You just don't care. 0, 1 topologically open set, it's topologically real line. So the complement of the Hopf link is T2 cross R. If you don't think about it, if someone tells you, look at this picture here of these two circles, think they are in S3. So prove that it is diffeomorphic to T2 cross R. What? It's not intuitive, right? And this is a simple link. This is a very simple link. So that's why we can make this argument.
Here.
Yeah, go with that.
Okay. So if we not instead of taking half link, we have to separate the links. Means separate two surfaces. Then
anything else? If you try to do any other example, you are gonna be in much trouble, because most of the manifolds, they don't have these product structures. T2 plus R is like triple product. Is S1 cross S1 cross R. You will end up something like, what is the complement of the figure 8 knot? Well, it's the complement of the figure 8 knot. There is no other way of saying this topology is that. There's no better way. So if you try to use other examples, you are going to be in a bad situation most of the times. I'm not going to even try to do any other example, because if you don't think of them before, they might be really hard. Okay, so here are some other examples. These pictures are Thurston's pictures. We have here the unknot, not hyperbolic. We have here the hot link, not hyperbolic.
Can I make a comment?
Sure.
Unknot actually, basically we are looking at finite volume hyperbolic things actually, right?
Yes.
Because of finite volume, the unknot does not become hyperbolic, in the sense that if you take the unknot and its complement would be disk across this one, S1, where actually you can put metric of coming to -1, but it won't be finite volume.
Exactly. Well, this is one of the manifolds actually that we remove when we are working with hyperbolization, with geometrization, because it has a hyperbolic metric, but of infinite volume. You are quotienting by, I think, just one translation, right?
Yeah.
You are quotienting by one parabolic translation, so you're going to have infinite volume. You have one end. This is very interesting. You have one end of infinite volume and the other of finite volume. Okay, so yeah, so we'll come back. So here we have some examples. The hot link, not hyperbolic, the unknot, not hyperbolic. So usually it's a lot easier to prove that something is not hyperbolic than to prove that something is hyperbolic. Like the hot link, I could prove that it's not hyperbolic just looking, yeah, here's the central annulus. Don't bother me. But the other ones, to prove that something is actually hyperbolic, might take a little more effort to go, because you need to rule out every possibility. Okay, so here we have pictures of some hyperbolic things. The Whitehead link, this one, the figure 8 knot is also hyperbolic, and here other hyperbolic things in S3. All these pictures are from Thurston's book. And someday I would love to understand what this E5 link is. It's beautiful. I would love to work something in this link. What is that? And why is there a 5? Probably because I have 5 circles somewhere, but it's a cool link. I'd like to understand it a little better, but I still don't. Well, having said that, I want to take the last half an hour, 40 minutes of the course to give you some personal account of why I work in hyperbolic geometry, why I got interested, and what I could manage to do research-wise about this. So what is left for research in hyperbolic geometry? So maybe some advertisement of the research field and my own research. Okay, so let me give you a few motivations to all the research that I'm going to present here. First, start with complete hyperbolic manifold of finite volume, and you have a surface of finite topology. So what is finite topology? It means that you have finite genus and a finite number of points removed. Like the plane. The plane has finite topology because the plane is just the sphere minus 1 point. Or you could have the torus minus 6 points. Or you could have any surface of genus G minus any number of points removed. but finite, everything finite. That's being finite topology. And I know I wrote here two-sided, but let's think that everything is orientable, the ambient space and the surface. And this surface is properly immersed in your manifold. So in 2015, these guys, which I admire a lot, Pascal Colin, Lohan Hauswirth, and Harold Rosenberg, they proved this result about minimal surfaces in hyperbolic two manifolds of finite volume. And that was the very first time that I heard the expression hyperbolic two manifolds of finite volume. I am a differential geometer, like with both feet in differential geometry. And I'm not topologist, so right here, from here on, everything's going to be more geometry than topology. And they proved this beautiful theorem, in my point of view. If you have a minimal surface, and if you don't know what a minimal surface is, I can tell you more or less quickly. A minimal surface is basically the analog, please, of geodesics. Geodesics are critical points for the length, but they might not be global minimums. They minimize the length locally, but maybe not globally. Minimal surfaces is the same thing for area. They are critical points for the area functional, but they might, and they are local minimals for a small region, it's going to be a minimum, but globally they might not be have minimal possible area. And one very important thing about minimal surfaces is that they have something called the mean curvature equals 0 everywhere. Just like geodesics have 0 geodesic curvature everywhere, minimal surfaces have 0 mean curvature everywhere. Okay, so what they prove is that if you have a minimal surface and you have finite topology and you are properly immersed in a hyperbolic manifold of finite volume, then you know how the asymptotic behavior of the surface is. They are asymptotic to a standard, totally geodesic annulus in some cusp-end of your manifold, and the surface will have finite total curvature 2 pi times the other characteristic. And they also proved, together with some people like in the 80s, existence of minimal surfaces, and also with Laurent Mazet, then added. This was 1 year later, I guess. They proved existence of embedded, properly embedded minimal surfaces, which are actually with smallest possible area in the isotopy class. Okay. So the first theorem that I started to work in hyperbolic geometry was a generalization of this theorem by Colin, Hauswirth, and Rosenberg. It's basically the same theorem, but for constant mean curvature instead of minimal surfaces. So if sigma is a constant mean curvature H surface in some hyperbolic manifold of finite volume, and the value of the mean curvature is in between 0 and 1, then again we have a description of the ends, asymptotic behavior of the ends, and they will be asymptotic to some standard ends, totally umbilic in your ambient space, and it will have finite total curvature 2 pi times the other characteristic. Here, this is Gauss-Bonnet theorem. So you're probably thinking, but why is it there? Why is it a theorem? The thing is, Gauss-Bonnet theorem works fine for closed surfaces. These surfaces are non-compact. So that's not always true. You will always have one direction, which is Convossen inequality, but equality might not hold. Okay. So what happens in particular is that the other characteristic of sigma is going to be negative, and there is no properly immersed constant mean curvature surfaces in these manifolds with mean curvature in the range 0, 1. And I should mention that 1 is a very special number here. It's called the critical mean curvature. So for H3 or hyperbolic tree space, 1 is what divides minimal surfaces. If you have constant mean curvature larger than 1, you have compact examples. If you have constant mean curvature less than 1, you don't have compact examples, closed examples. Okay, but we were worried because we had a theorem about some object, but we didn't know any example. We didn't have any examples of a properly immersed constant mean curvature in the range 0, 1 positive in hyperbolic manifolds of finite volume. The only example we could cook up in the, like almost publishing the paper was very silly example. And well, but there is, at least it existed. And the main question to us became, what are the values of H and topological types that appear as properly immersed or properly embedded surfaces of constant mean curvature H in some hyperbolic manifold of finite volume? So this is our second main result. We called Colin Adams to work with. Colin Adams, he is a topologist. And our construction, I will present the construction in a few seconds, 2 minutes. It was more or less like this. You need a totally geodesic example. If you start with a totally geodesic example, then you can take parallel surfaces to it, and they will have constant mean curvature, positive constant mean curvature. So we knew that if we had a totally geodesic example in a hyperbolic manifold of finite volume, then we would have constant mean curvature examples in the same ambient space. So we basically talked to Adams and asked him, what are all the totally geodesic examples that exist? And he said, well, I don't know. And when you have a question and you don't have an answer, that's where mathematics happen, right? So that's where research happens. So our main theorem in this paper goes more or less like this. Given any value of the mean curvature between 0, 1, and any abstract surface S of finite topology and negative Euler characteristic, which is the admissible topologies that exist. So there exists a complete hyperbolic manifold of finite volume and a complete proper embedding of S to end with constant mean curvature H. So anything that can happen actually happens. And this embedding actually can be chosen to be totally umbilical. So here's the construction. I'll give you the outline of this construction, and then I will give you a few properties. Okay, so first, you fix your value of the mean curvature and you fix your surface S. First thing, you find a totally geodesic example in some hyperbolic tree manifold of finite volume, and you need some nice properties of this totally geodesic example. Then, as I said before, you look at the parallel surfaces to this surface, and by parallel, I don't mean equidistant, because remember, we are in these manifolds where you don't have much space at infinity. At infinity, everything is like really short. The cuspans are small. So there is no positive distance to anything in the ends. By parallel, I mean, take the surface, take the normal vector orienting the surface, and move it through the normal vector. So you look at these parallel surfaces to sigma, and they will have some properties. The first one, they have constant mean curvature equal to hyperbolic tangent of t, and this number converges to 1 when t goes to infinity. So they will have all the ranges of the mean curvature that you want. Every one of them is properly immersed. And this was really, really what got our model running. Like, you are in a space where you don't have space at all. You take something which is properly embedded, and that should be really specific. Then you go parallel, and it's proper. When we figured this out, and it's easy to see that this is true, actually, we said, wow, there's something there. And for small values of t, so in particular for small values of h, it's not going to be just properly immersed, but properly embedded. So it's even better than we were hoping for. And then this gives the theorem, this gives the theorem for small values of h, but now we need to get to this value of h. So you see how far you want to go. I want to go up to 10. I want to be able to move my surface 10 units and remain embedded. And you assume that you can't. If you can't do that, we will build a finite cover of our manifold. And in this finite cover, our totally geodesic example will lift. And in this new manifold, you will be able to walk 10 units. And it's going to be properly embedded for 10 units, and then you have your theorem. Okay, and here's where I can explain, go back to topology. Everything here was geometry in this part of the talk, really geometric. And now I go back to geometric topology, where we construct the totally geodesic example. So the theorem is more or less like this. You have your surface of finite topology. So you have genus G in n ends and negative Euler characteristics. So there is an inequality here. 2 minus 2G minus n is negative. So we can find a hyperbolic tremanifold of finite volume, which admits a proper two-sided embedding of this surface S into n with totally geodesic image sigma. And they will have some nice properties, which are the sigma won't separate your ambient space. Distinct ends of S will embed in disjoint ends of your ambient space. And this is the most important thing, your surface will be in the fixed point set of an order 2 isometry of your ambient space. You have a hyperbolic tremanifold of finite volume, and it will have a reflection. And your surface is going to be in this fixed point set. So there are 3 cases to consider. The first one is genus 0. So this inequality here, if G is 0, you get n larger than 2. So n is bigger or equal to 3. And that means you need to construct a sphere with 3 or more punctures. If genus is 1, this is the hardest case. Genus 1 surfaces in hyperbolic tremanifolds. Well, genus 1 is torus, right? Tori in hyperbolic tremanifolds are weird. They are the hard case always. And now we need a tori with 1 or more punctures or higher genus surfaces with any number of punctures. Okay, so let me give you the explicit construction in the genus 0 case. And this is really simple, really simple. You start with S3, is your P manifold, your ambient manifold, and you look at one S2 plane. So this plane here is S2 inside of S3, like, and you have a reflection, right? You have some map which maps the interior of S2 to the exterior of S2. Basically, you interchange these components. Now, you take any number 3 or more of circles, and you remove the circles, and you look at these blue curves here. You have here, in this picture, you have 4 blue curves. You are removing 4 disks from S2. Now you want to create a hyperbolic link in this manifold. This is not hyperbolic by several reasons. The easiest one is that it has essential disks. This white things here, they are all essential disks. But this is also unlinked, so you have essential spheres too. It's not even irreducible, this manifold. So we need to kill these disks we need to kill these spheres, so we need to link these blue curves without losing symmetry, without losing this reflective symmetry. So we can do it the easiest way you can imagine. Just add to this link these red circles. Think here is S2, horizontal. All the curves are horizontal. And now you link any two curves by a reflective symmetric S1. Here, back, and you close up. This is one of those examples that I showed you before. This is a chain. This is called the daisy chain. And the daisy chain is well known. The daisy chain is hyperbolic if and only if n is bigger or equal to 3. So Thurston knew that, and we can just use it. This manifold here, the complement of this manifold is going to be a complete hyperbolic metric of finite volume. It has this symmetry, and this symmetry is actually an isometry. And now inside this manifold, you have exactly this highlighted surface, which is S2 minus 4 disks. So S2 minus 4 points. So taking notice that these red curves do not intersect your gray surface here. So you remain symmetric, and you have one surface which is a sphere minus any number of points that you want. And basically that's it. And bigger or equal to 3 implies that it's hyperbolic and it's complete. And the restriction of this reflection to your manifold is actually going to be a isometry of your manifold. And here, this word muscle, this name, I should mention. Hyperbolic geometry is a field by itself. You could spend years and years and years studying all the nice properties of hyperbolic manifolds of finite volume. And there are several good references for that. For instance, the book by Petronio, Italian guy, and I forgot his collaborator. Petronio and Benedetti. Perfect. Benedetti Petronio is one of the main references to geometric properties of hyperbolic manifolds. So yeah, let's give you just a recap. We fixed the topology, in this case, genus 0 and 3 or more n's. We chose a closed hyperbolic, closed tree manifold. In this case was S3. And we looked at a closed surface in this manifold, in this case S2. And this closed surface was in the fixed point set of reflection. And we found a hyperbolic link in this manifold such that a complement of this hyperbolic link in the surface was diffeomorphic to whatever we wanted, and that this reflection would restrict to an isometry of your manifold. So the bad news, which is not bad, it's actually good, is that to find this in general is not so easy. And it's good news because then you have research to do, right? But it's bad because it's hard. But when you can do it, it's fine. So the strategy is to prove some base cases like genus 1 and 1n, or genus 0, or genus bigger or equal to 2 and 0 n's, and use some induction process on the number of n's. These pictures show the base. These pictures show the base of induction that we are going to need. This first picture here is you take your genus bigger or equal to 2 surface, and you multiply it by S1. So here you have bitorus times S1. And this is a trefoil knot, so this picture isn't actually good. This should be something called a fully alternating link in this manifold. And what we can show is that if you reflect this fully alternating link here, this manifold is hyperbolic, the complement of this fully alternating link, this fully alternating and the reflected image of it, it's going to be hyperbolic with finite volume, and it will have these two surfaces here as totally geodesic surfaces. And here is something.
Yeah, I have a question here. You draw the link diagram on the genus 2 surface.
Say it again, please.
You have drawn the trefoil link diagram here in genus G cross S1. So the diagram, where is the diagram? Where we project the link or not? Not the trefoil, not.
No. This is just a representation. It's not going to look like that because we need a projection on this genus 2 surface. We have here genus 2 surface and times S1. So the real picture of it would need a projection in this vertical surface, genus 2. So we would see like one curve here going around this genus 2 surface. And it wouldn't be one curve, we would need a link here. So it's not an easy picture to draw. That's why I didn't draw this picture. Okay? And so this other thing here, it's harder to obtain. This one was already available. The technology to create this example was already available, but the technology to create this example was not available. And I don't want to go into details of how you create this other manifold. It's a whole 20 pages just to create this example. Okay, so the thing now is an induction of the number of ends, preserving hyperbolicity and symmetry. And then we obtain this called the moves, preserving hyperbolicity of link complements. So this is where I really needed to learn hyperbolic geometry from a geometric topology point of view. This is where we used Thurston's hyperbolicity criterion. You have a link in a trimanifold, and there is some hidden hypothesis here. Never mind this hypothesis so far by now. You have a link in a closed trimanifold, and we assume that this link is hyperbolic. And our idea was to modify this link, preserving hyperbolicity, and making a new link with properties that we like. So there are actually two theorems in one here. Assume that there exists a ball in your manifold P, which intersects the link either like this or like that. So this ball in this example here would be something that goes around like this. And in the second example, the ball would be a neighborhood of this circle here. So we have a ball in your ambient space P that intersects either like two arcs or like this tangle here. And these two arcs here, they need an extra hypothesis, but I'm not going to give them to you because it's not going to be very important. Okay? So if we replace inside this ball, whatever the ball is intersecting of the link, in this case, we replaced by this tangle, and in this case, we replaced by this tangle. So we make it a little more complicated, but in a, how to say that, in a controlled manner, then we know that the resulting link is hyperbolic. So we can modify our link to keep hyperbolicity. Okay? And what's the good point of view here? If we are, in this case here, without any punctures, and then we use what we call, this is the switch move. Now we have one circle that we can put exactly here. And now you have S2, you have S2, you have SG, a surface of genus G minus a disk. So you added one end to your surface. Then you can again take this tangle, which is the same, and you add one more puncture. And again, in this small neighborhood, you will see that this picture repeats. So you can add one more puncture, and one more puncture, and one more puncture. I'm not going into the details of anything here, because it's not going to be productive at all. But that's the main idea, and that's why I had to learn Thurston's hyperbolicity criterion, because what's the argument for these proofs? The argument for these proofs are more or less like this. You have a link in your manifold, and you want to prove it is hyperbolic. So how do you do that? You go for essential spheres. Are there any essential spheres? Are there any essential disks? Are there any essential chloride? And are there any essential anyone? And the thing is, if you have an essential something in your next manifold, in your L prime link complement, you want to show that this object, or at least some object similar to it, exists in your previous manifold. But your previous manifold was hyperbolic, so it couldn't exist. And that's where Thurston's hyperbolicity criterion comes in handy. Okay, so I think I will stop here with this last quote of William Thurston. I love the day that I read that, I said, yeah, go geometry. It's more or less like this. To most topologists at the time, hyperbolic geometry was an arcane side branch of mathematics. He's talking about his day, like 70 something, 80 something. Although there were other groups of mathematicians, such as differential geometries. I was not included back then, but today I couldn't understand it from certain points of view. Hyperbolic geometry, from the point of view of geometry, was more or less developed already, although we didn't have many examples. This is something really that only mathematics can produce. Okay, so thank you again. If you need something, just send me an email. I will probably tomorrow put the slides on my website if you want to download it from there. So thank you. And before I forget, I would like to thank deeply ICTP and SIMPA for the funding and opportunity to be here and give this course. And are there any questions? Let's see. Chat. The C, you can get the slides on my website. Tomorrow I will, well, probably you shouldn't let everyone see your email. It's gone. I'm sorry. But yeah, they will be on my website. I cannot copy your email right now. So if there are no questions, thank you all again.
I have a question.